right, good morning, which is when you'll see this morning. We are doing our first review, and for AP Biology, it'll cover chemistry, including bonding, covalent, ionic, hydrogen bonding, water chemistry, carbon chemistry, building and breaking down polymers, dehydration, synthesis, and hydrolysis, and lipids. And carbohydrates. I don't know that we'll have a chance to get into proteins. If we do have time, then we will. If not, then that'll be the next video. If you're following along with your notes, this was our very first unit. Up the top it says chemistry and biochemistry. In our book, if regardless of whether you're in the first or second edition, it's the second and third chapters. So to start off with, we wanted to look at bonding just a little bit. It's unlikely that they're going to ask you the definition of a covalent bond or an ionic bond, but knowing how they work helps you a lot later on. Hydrogen bonds seem to come up quite a bit. Hydrogen bonds hold, that's what attracts water molecules to other water molecules, cohesion. It's what holds the left and the right half of DNA together, like A's to G's and A's to T's and G's to C's. And so it is important. So we'll start off with a little bit of bonding. If I look at a periodic table, I'm going to zoom in on this periodic table. Try to get that light out of the picture some. So if I look at this periodic table, one of the things that we probably remember from chemistry is these are the noble gases. They tend to be, there we go. The noble gases will tend to be stable, so they're never trying to gain or lose electrons. They're perfectly stable. If I'm right here, if I'm fluorine, for example, I have 1, 2, 3, 4, 5, 6, 7 valence electrons. Remember, valence electrons are the outer shell. Because they're the outer shell, they're the ones that determine bonding. If I had like 3 or 4 rings of electrons, the outer ring is the one that I'm going to bump into some other chemical with to see if we actually have any interaction. So right here, fluorine wants to gain 1 more. Oxygen, since it's 2 columns over, wants to gain 2 more. If I was sodium, I want to get rid of an electron. So in general, things over here want to get rid of electrons. When you get rid of electrons, you become more positive. So they want to get rid of 1. So that means there'll be a +1 column. They want to get rid of 2. Calcium wants to get rid of 2. So that column will be +2. Over here, they want to gain 1. They want to gain an electron. When you gain an electron, electrons are negative, so you become negative. So in general, when something from the left and something from the right side of the periodic table bond, that's an ionic bond. When something from the right and something else from the right bond, that's a covalent bond. In ionic, because somebody is getting rid of electrons and somebody is receiving them, when you get rid of an electron, you just became plus. When you gain it, you just became minus. So that's why sodium and chlorine, the sodium will have a plus, the chlorine will have a minus. Over here, everybody wants them. So if I was going to bond a nitrogen and an oxygen together, they're both trying to gain electrons. So they have to share. That's a covalent bond, is sharing electrons. Okay, one other thing that I'm going to go ahead and show you really quick, because I'm going to zoom out in a minute, but this is a periodic table based off of electronegativity. So let me go ahead and move the video camera back. Like this. Okay. So now we've got ionic bonds. That's when somebody gives and somebody receives an electron or electrons. Covalent is when you share electrons. And then hydrogen bonding is something kind of different. We're going to bring it up as we talk about water. So let's say that we've got a water molecule right here. The shape of water is bent. And those solid lines, that represents a covalent bond. Solid lines always represent covalent bonds. You might have single or double covalent bonds, as you can see down here, maybe. But a solid line is always a covalent bond, sharing a pair of electrons. Okay, now here's what's unique about water. Well, not totally unique. It's a unique property of water, but there are other things that have this property too. So I guess it's not unique. So here's a water molecule. That's a covalent bond. However, according to this chart that's showing electronegativity, as we go to the right and up on the chart, we increase in electronegativity. Well, what's electronegativity? Electronegativity is how strongly you attract electrons. Technically, electronegativity is within a molecule. Electron affinity is between molecules. I'm not in biology, we're not that concerned about it, but that's technically the chemical proper definition. So within this molecule, one of these guys, oxygen or hydrogen, might attract electrons more strongly than the other. Well, the most electronegative thing is fluorine, because it's at the top right. Again, we ignore noble gases. They're not trying to hog electrons at all. They're noble gases. They're stable. So fluorine has an electronegativity of 4. Oxygen is 3.5 in second place compared to everybody else. That's important. So oxygen is the second biggest electron hog on the periodic table. So when we're talking about water, they do have in the curriculum for AP Biology, they do mention quite a few things about water, so we're going to walk through that. Even if they don't ask directly about water, the properties of water help explain all kinds of things like cell membranes and stuff like that later on. So here's a water molecule. The first thing that we look at is that oxygen has a higher, that's an O with an arrow going up. Oxygen has a much higher electronegativity than hydrogen. So hydrogen is kind of higher. Oxygen is kind of higher. Oxygen is higher and hydrogen is lower. Oxygen is 3.5, hydrogen is 2.1. So what that means is even though that's a covalent bond, they aren't sharing the electrons equally. A covalent bond is shared electrons. They aren't sharing that pair of electrons equally. I tell my students it's like if I go to a movie and I'm sharing a Coke with my son, he shares Coke like oxygen shares electrons. So I'll give him the Coke, he'll be like slurp, 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 slurp. I take one slurp and he's got his hand out. Slurp, 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 slurp. Kind of like that. And so because of that, what we find is the electrons, we don't know that electrons orbit like planets. There's no evidence that they do. But pretend that they did, because all I've got is a whiteboard and a marker. If the electrons were evenly shared, they'd go like this. They'd spend about half their time around oxygen and half around hydrogen. But they're not. Oxygen is way more electronegative, 3.5, compared to hydrogen, 2.1. You don't have to memorize those numbers. So the electrons do this. Oxygen, 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 hydrogen. You, me. You, and then you share with me. So because of that, overall, the effect is that oxygen has a slight negative charge on it, and the hydrogens have slight positives. Why? Well, electrons are negative, so if the electrons are spending a bunch of time around oxygen, then of course that'll be slightly negative, and they're spending less here, so relatively speaking, that's slightly positive. Even though we're still only sharing negatives, if I've got 80, if I'm negative 80 in my bank account and you're negative 10, you still have 70 more than me. You're still plus 70 compared to me. So even though this guy still has some negatives hanging around him, that guy has more negatives, so he is more negative. Well, when we see slight negatives and slight positives, that's opposite. And in chemistry, we call opposites polar. So because of this difference in electronegativity, because it's big enough, water is polar. Meaning, one side has some negatives, another part or parts have positives. North and South Pole on the globe, they're opposites. If somebody has bipolar disorder, they go from highs to deep depression. So polar means opposite. Okay, well because of that, a few other things now happen. So if I've got a few water molecules next to each other, here's one, here's one, here's one. That hydrogen and that hydrogen, they're both slightly positive. They'll repel each other. So that water molecule will actually move up or move down, or this guy will move up or move down. So water molecules kind of automatically sort of form this lattice-looking structure, like that. And what's holding them in place is that slight positive of that hydrogen and that slight negative of that oxygen. They're attracted. Opposites attract. And so they form, what I'm doing is I'm drawing a dotted line, and that dotted line is an H bond, a hydrogen bond. Hydrogen bonds are always dotted or dashed lines. We said earlier, covalent bonds are always solid lines. So within a water molecule, within a single water molecule, covalent bonds. Between water molecules, hydrogen bonds, right? That's sort of like within me, intrapersonal skills versus between interpersonal skills. How do I react with other people? So within a water molecule, it's covalent. Between water molecules, it's hydrogen bonds. Well, because of hydrogen bonds, what is that called when water sticks to water? Cohesion. So water is attracted to water. They stick to each other. Water will also stick to other things that are polar. That's called adhesion. So if water sticks to something else that's not water, that's adhesion. If chemical X sticks to X because of hydrogen bonding, that's cohesion. If X sticks to Y or Z, then because of hydrogen bonds, that's called adhesion. Okay, so the chemical reason, there might be some physics reasons too with like surface area and plating and stuff like that. But if I have a piece of paper towel and I stick the corner in water, the water travels up the paper towel. If I do the same experiment with wax paper, the water does not travel up the wax paper. The reason why is paper is polar. We're going to assume that it has some positives and negatives on it, slight positives, slight negatives, and so water is attracted to it. Whenever I put wax on there, wax is nonpolar. We'll learn what makes nonpolar things nonpolar, or give some examples later. But when I put wax on paper, then now the water is not attracted to it, because polar and nonpolar things don't mix. Okay, so also because of hydrogen bonds, because of cohesion and hydrogen bonds, we also have what's called surface tension. And because all the water molecules are kind of holding hands, so to speak, with hydrogen bonds, I can now, if I've got all these water molecules and I put like a paperclip on top, the paperclip might float, even though whatever metal the paperclip's made out of, aluminum or whatever, might actually be more dense. Kind of like crowd surfing. If we all hold hands or whatever, then the person's not going to fall through. But if we just stand like this, they'll just go right between us. So surface tension. This also is why it takes so much energy to heat water up. We say that water has a high heat capacity. Has a high heat capacity. Heat capacity is high heat. And that's because if I want to heat water up from 70 degrees to 75 degrees to 80 degrees, or eventually 212, and it vaporizes Fahrenheit, then I'm always, if water molecules are going to move around faster, they're going to have to break hydrogen bonds. But as soon as I break off from this neighbor, I bump into this neighbor and form a new hydrogen bond. So then I have to break off of that one. So that's why it takes so much time to heat up water. In a chemistry class, it's something like the amount of energy it takes to heat up 1 milliliter of water, 1 degree Celsius is specific heat, and then like heat of vaporization is energy to actually make it vaporize. But together we call those high heat capacity. The very last thing that matters about this is transpiration. So if I've got a tree, beautiful tree by the way, a little stubby, wood is naturally pretty porous. That's why if you had a glass, this is not a glass, but if I did have a glass and it was sweating, and I put it on the end table at my house, I might get yelled at by a parent because that wood, if it doesn't have a special coating on the top, it'll just soak up the water and leave a ring, because that's what trees do, they soak up water. So essentially what will happen is root all the way up to the leaves is pretty much sort of like a system of straws. And so inside the straw, the xylem carries water. Inside these little tube-like straw things, xylem, the water molecules are adhering to the side. So they kind of go up like this. But then because of cohesion, they're dragging up the last water molecule with them. So it's almost like if I had 100 students attached to me with hydrogen bonds, if I move to the left a foot, they all move to the left a foot, because we're all hydrogen bonding with each other. So if this water goes up to this leaf and let's say it evaporates, then it just pulls the next guy up in line. We pull the next guy up out of the ground. They call that transpiration. Also because of cohesion and adhesion. So the thing that's interesting about this is like, well, why is there a high heat capacity? Well, because water is cohesive. Why? Well, because each water molecule has hydrogen bonds between it and its neighbor. Why? Because each water molecule is polar. Why? Because oxygen hogs electrons more than hydrogen does. So this is how we want to remember biology stuff. Because of this makes sense. Because of that, this makes sense. Because of that makes sense, and that makes sense. So it's sort of like a big story. So yes, it's a lot of information, but once you know one or two things, the rest of it just kind of falls into place. That's how we want to focus on learning biology in here. Below that, we talk about carbon, versatility of carbon, building macromolecules, and carbohydrates. One thing that I wanted to mention, they're never going to ask you this on an AP Bio test either. How many bonds does a stable atom of carbon always form? It's 4. It'll help you in college to know that. Hydrogen is 1. And it also helps you with a lot of stuff in bio. Even though we never make you know that exact random detail, it actually becomes really useful. So we're made, living things, that is, are made primarily out of chunks. And we're held together with mostly covalent bonds. Covalent bonds can be pretty stable in water. Ionic bonds, because they're positives and negatives, they tend to dissociate. Not associate, but they tend to dissociate in water. With COVID-19, we're supposed to be distancing ourselves, dissociating from other people, not associating and grouping together. So if I put sodium chloride in water, table salt, it'll dissociate into sodium positive ions and chlorine anions, negative ions. Okay, but we're mostly chunks. So most of our bonds are going to be covalent. Yes, we still have sodium and chlorine and potassium and calcium so that our nerves can work and then our muscles can contract. But carbon always forms 4 bonds. Hydrogen always forms 1 once they're stable. If somehow carbon had 5 bonds, it would just be for a moment, because then to become stable, it would get rid of 1. Almost like if I could call this green expo pen into being, floating, it's not stable there, so as soon as it comes into being, it will fall. So same thing, carbon will eventually have 4 bonds when it's stable. Okay, so the next part that we want to look at is carbohydrates. And once we look at carbohydrates, then we'll kind of come back and get that little part about building macromolecules. So carbohydrates. Let me erase all this. For carbohydrates, you can have monosaccharides or disaccharides or polysaccharides. I'll leave that. The main thing that students would need to be able to recognize for carbohydrates are these 2 primary shapes. Pentagons or hexagons with an oxygen in the corner, probably going to be a carbohydrate, and the name will probably end in ose. Maltose, glucose, fructose, those are carbohydrates. Okay, so let's say that I've got glucose. So I'm going to draw a version of glucose. They get into alpha and beta and all that. We aren't worried about that at the moment. So I'm going to draw one of the versions of glucose. Now, I'm only going to draw the stuff hanging off the ends, but what do I know has to be in the middle of that? That has to be a carbon because I have 1, 2, 3, 4 bonds. Here I have the angled one, the vertical, and the horizontal. So that's 4 bonds. So that has to be a carbon. So we often don't write our carbons in just because it's obvious if there's a 4-way intersection that there's a carbon there. Okay, so what do we assume is at the end of all these dead ends unless I tell you otherwise? Hydrogen. Hydrogen always has 1 bond, so we don't even bother writing them in. If it's a dead end right there, you just assume it's hydrogen unless I tell you otherwise. So what I'm going to do is I'm going to look at this one version. Let's see, OH, H, OH, H. Again, there's other stuff hanging off of these, but I don't care. I'm just looking at the edges. If I have a simple carbohydrate and another simple carbohydrate, then what I want to do, let's say I want to join them together. I want to take glucoses and join them together to make starch or to make chitin or glycogen. Those are all polymers of glucose. Mer means part. So polymer means many parts. So if I have a monomer of glucose and another monomer of glucose and another, eventually I have many parts. So I'm building a polymer out of 1, 2, 3, 4 monomers. Okay, so the way that I join these things together, whether I'm joining carbohydrates or joining amino acids to make a protein or nucleic acids, if I'm going to join some nucleotides together to make a string of DNA or RNA, we have two major processes. Okay, so first off, let me back up. To join, we have one process, and to break down, we have one process. We have two major processes, one for building and one for breaking them down. So over there, I've got 4 bonds coming off, so there has to be a carbon. 4 bonds coming off, so there has to be a carbon. If I want to join this glucose and this glucose together, then I need another covalent bond. There we go. Great. What's wrong with this picture? Now that carbon and that carbon each have one too many bonds. So what's going to happen is if the brown one stays, I have to get rid of one of the green ones. So if I get rid of that bond and I get rid of that bond, now this carbon is stable again. 1, 2, 3, 4. Angle, angle, vertical, horizontal. So they each have 4. But what about these guys? They now go together. I have an H, an H. I have an HOH. I have H2O, water. So when that H and that OH join together, that makes water. So they call this process dehydration synthesis. Dehydration synthesis. Word makes sense. Synthesize is to put together. I just put these two things together. So this is synthesis. Dehydration means I removed water. I removed water in order to put two things together. Dehydration synthesis. So that's how I join carbs together to make a polysaccharide. That's how I join amino acids together to make a protein. That's how I join nucleotides together to make DNA or RNA. Okay, what if I want to break those things apart? What if I just ate some peanut butter and I want to break it down into individual amino acids, or I just ate some starch and I want to break it down into individual glucoses? Well, now we just do the opposite. So now we do what's called hydrolysis. What does hydro mean? Yeah, water. What does lysis mean? Like lysosomes, L-Y-S, not L-I-C-E, that's in your hair. Lysis means to split apart, so this means water splitting. So essentially what we do is water splitting. If I have an HOH, a water, then I could take this OH, I'm going to split my water, I'm going to add an H there, and I'm going to add the OH over there. So I split water, and I joined those parts, that OH and that H group, in this hydroxyl group. But now this carbon has one too many bonds. So if this bond goes away, then with hydrolysis, then now I split this apart due to hydrolysis. That's how we break apart chains of amino acids or chains of carbohydrates. As far as the major functions of carbohydrates, they tend to be short-term energy. They can be longer-term, but they tend to be more short-term energy compared to lipids, but not as short-term as ATP. So ATP is super short-term. I guess we could say that carbohydrates are more medium, if I'm going to have 3 things to compare. 3. And lipids are more long-term typically. But they can also be for structure, like cellulose. That's in plant cell walls. That's why it's harder for us to just digest plant material. So carbohydrates. Okay, the next part that we want to look at are lipids. Let me check something really fast. Okay, we're at, so 4:15. Okay, so the next thing that we want to look at, lipids. There we go. So you might remember this picture from class. That is a triglyceride. That's a glycerol molecule with 1, 2, 3 fatty acid tails. And then if I can maybe zoom it in one more click. If I look at it closely, everything looks nice and even. What you'll notice is every single carbon along there has single bonds. Ignore the glycerol part, but on the fatty acid tails, every carbon has single bonds. Let me make sure you can see that, okay? And we'll zoom it in a little. There you go. So they all have single bonds. In this picture, we now notice there's a change in shape. And I don't know how well you can see it, but that's a double bond right there. And when we got a double bond, we also got a kink. So one of these is called saturated, and one of these is called unsaturated. All right, let's go back where we were. Okay, so now, how is it that I know which one is saturated and which one is unsaturated? Well, if I take my glycerol molecule here, so glycerol is just going to be represented by this rectangle. Whenever I have a fatty acid chain with all single bonds, it's holding the maximum amount of hydrogen possible. It's saturated with hydrogen. But if you take a tail, and let's say that all of a sudden, so here we go. Hydrogen, hydrogen, hydrogen. I know all those dead ends have hydrogens. I'm drawing the carbons, but otherwise I would normally just shorthand, I would show it like this. Okay, so if I go in and I add a double bond, let's say I change this single bond right here to a double, so I'll make it a different color. Now that carbon has one too many bonds. Same with that one, so they have to get rid of a bond, which means they just lost a hydrogen, just lost another hydrogen. So now I'm not saturated with hydrogen anymore. So now that tail would be called unsaturated. And with these fats, if I have one double bond, then I'm unsaturated once, we call that monounsaturated. So saturated just means you're full of hydrogens. Another thing you'll notice is whenever I get in a double bond like that, I tend to get kinks. Now, if you go on a deeper dive into organic chemistry, there's cis double bonds and trans double bonds. Trans tend to stay straight. Cis double bonds add kinks. You might have heard of trans fats in foods, or hopefully not in your foods now. So whenever I add double bonds, I add kinks. So what that means is overall, if I look at the structure of a saturated fat, it's kind of more like a capital E. It looks more like this. So these are saturated fats. If I look at an unsaturated fat, the tails are a little bit more crazy. Crazy E's. Okay, so you might have heard that one of these tends to be considered more bad for you and one tends to be better. They both have the same number of calories. They're both super high in calories. But let me ask you this. Which one tends to be more solid at room temperature? Saturated, unsaturated? It's saturated. And that's logical because that has a regular shape, so I can pack those together. Just like if these were boxes or something I had to stack, I can pack a lot into a small space. These are kind of more unwieldy, so I can't pack them together as closely. In chemistry, one of the ways that you can look at a solid, this isn't perfect, but in general, a solid is if if things are close together, packed close together, that's a solid. Not as close, that's a liquid. Not close at all, that's a vapor, right? That's a gas. So that's more solid, that's more liquid. Animal fats are more saturated, more solid, right? If you look at a piece of steak and there's a hunk of white fat on there, it's solid. If you look at bacon, uncooked, That white stuff on there, that's fat and that's solid. But if you look at olive oil or corn oil or canola oil, those are all oils, they're liquids. So the reason that for a long time we always considered these to be generally more or worse for you than these is because these are more likely to clog your arteries. It's not quite that simple, but this one is more solid. Now the thing that's interesting is carbon and hydrogen have similar electronegativity. So if I go back and look at a periodic table, my electronegativity periodic table, I know you can't see it, but carbon has an electronegativity of 2.5. Hydrogen is 2.1. Chemists will say, hey, 2.5 and 2.1, that means they're sharing electrons equally enough that nobody's really slightly positive or really slightly negative enough to matter, so they're non-polar. Again, oxygen was 3.5, hydrogen was 2.1 with water. So oxygen hogs electrons hard compared to hydrogen, so slight negative, slight positive. C's and H's, it's pretty much even. So these C's and H's up here, they're sharing electrons equally enough. Obviously the carbons and carbons are sharing equally because they're pulling with the same strength. So because of that, lipids are non-polar. Well, polar things and non-polar things don't mix very well. So if I take something like a fat, like bacon grease, and I try to mix it with water, it doesn't. All the water molecules are pulling together. They're cohesive. I erased it. But they are cohesive, and so they're excluding the oil or excluding the animal fat. If you think of it this way, pretend, it's kind of a dumb analogy, but think of like billiards, like pool balls. If all the even ones were attracted to each other, they would all stick, and then all the odd numbered ones would just be like kind of left on their own. So when you see oil and water not mixing, what it is water is holding on to water, and then the oil is just all mutually excluded. It's not that the oil is attracted to the oil, it's just that they're excluded from the water. So this is lipid, this is lipid. Neither one dissolves in water very well. My blood is a water-based liquid. So does either one of these fats dissolve in my blood very well? No. When I eat fat, I squirt that fat into my bloodstream as is, just teeny tiny. I physically break it down, but I don't chemically break it down before it ends up in my bloodstream. So I just physically hack it into smaller and smaller and smaller fat droplets. And then I dump it into my bloodstream. Now I don't dump it in completely as is. We can wrap it in various proteins to help deliver and help it be a little bit more soluble, but they don't dissolve very well in my bloodstream. So this one is solid and not dissolving in my bloodstream, and it's sticky and gooey. This one is not. Who's more likely to clog my arteries? Well, this one. If I have a gallon of olive oil, I can probably turn on the water in my sink in my kitchen, dump it down the drain, and be okay. But if I have bacon grease and I dump it down there, it's probably going to clog the drain because the water won't wash it away and it'll stick to the pipes. So this will stick to my pipes more. So let's go back and look at that. Saturated fats are more likely to clog my arteries than unsaturated fats. Why? Well, they're solid. Why? Well, because of their chemical structure. They have all single bonds. They're saturated with hydrogen. So all of their chemical structures are pretty straight, so I can pack them together, and that's the definition of a solid. Why does it clog my arteries? Well, it clogs your arteries because those don't dissolve in water very well, and your blood is a water-based system. This one doesn't dissolve in my blood very well either, but it's also not going to clog as much, just like olive oil won't clog the pipes. This is not the only way that you clog your arteries. It also depends on the condition of your arteries. The lining of your arteries can be super slick or really rough. So it's almost like if the pipes that I'm dumping bacon grease into, even if I have saturated fats, if the lining of the pipe is super, super slippery, they don't stick as much as if it was rough like concrete or something like that, like if I had concrete pipes. I don't know. So that's where we get into like, it's not just what you put saturated or unsaturated fat into your body. It's also what's the condition of your arteries. And that's where we're starting to think that like insulin spikes, blood sugar spikes might cause inflammation, and other things might cause inflammation inside of your arteries. So it's a combination of what kind of crap is floating around in there, and then what's the condition of the arteries as well. But pretty interesting. The last thing that I wanted to mention about lipids, would be that their main function is for energy storage. Actually, now I think about it, I said it a little bit earlier. Let me double check my notes real quick just to make sure I didn't leave anything off. I did want to go back and look at this. You might remember earlier in the year, moms that took thalidomide for their morning sickness tended to have kids with birth defects, limb deformities. This drug was more common in Germany. It was not common in the US, so this did not happen to very many US kids back in the day. I can't remember when it was. I want to say it was somewhere around the 40s, 50s, somewhere in there, but again, you'd have to Google that. I'm not exactly sure, but it wasn't like the 1800s or something like that. It was like 1940s-ish. So what happened with these babies was this. This is thalidomide. This is also thalidomide. They look like they're the same, but they're not. They're mirror images. And so you might remember we talked about isomers earlier in the year. There was left-handed methamphetamine and right-handed methamphetamine. Left-handed methamphetamine, levomethamphetamine, is found in vapor inhalers. And then right-handed meth is like crystal meth. That's obviously a very addictive drug. So the difference between these was isomers. When I ask my students what is C6H12O6, you guys always default to glucose. If somebody asked me as a biology teacher, that's what I would default to also. But it's also the chemical formula for fructose, C6H12O6. It's just all how do I arrange those C's and H's and O's. And so a different structural shape makes a huge difference. Chemistry in your 10th grade chemistry class versus chemistry in biology class, that's one of the major differences. In your 10th grade class, you're always trying to figure out the ratio of atoms. Like, okay, it'd be H2O, it wouldn't be H5O, that wouldn't make sense. Or, it's PO4 or PO3, is that phosphate or phosphite? You're always trying to figure out how many atoms you have. You're balancing equations and predicting equations. In biology, we want to know how are those atoms put together? What shape do they make? Because shape matters. So, the analogy that I gave you guys way earlier in the year in our first unit was this. Now you have a better understanding of receptors, so this analogy will make a little bit more sense. So let's say on the board, I have a receptor. And that receptor is supposed to bond with this chemical. So that means this chemical is called, a ligand or a ligand. I hear ligand the most. I don't know that ligand is actually wrong, though. So right now, green, purple, red. Green, purple, red. So here's my ligand, this is my receptor, and these are the binding sites that fit the ligand. It wouldn't matter if this was here or not. My receptor couldn't tell the difference. So purple goes with purple, green goes with green, red goes with red, and we line up pretty well. Pow. That receptor and that ligand fit. Now, if I take this and I just rotate the green and the purple, now I have a different version. This is an isomer. Same atoms, they're just arranged differently. So now it seems like I could hold it or spin it in a certain way to where I can still fit, but I can't. Anytime the purple and the green go together, the red is out there, up top. Anytime I get the red and the green, the purple's out here. Like I can't make it fit. It seems like my right foot could fit into my left shoe. I could just twist it the right way. Or it seems like if I had a left glove that I could put my right hand into it, but I can't because it's an isomer. So isomers are whenever you take the same chemical structure like C6H12O6, just rearrange the atoms, and now you have a different result. For example, with ibuprofen, typically the left-handed version of chemicals that's what they call them, left and right, levo and dextro, and then dextro is right. Whenever you are looking at like ibuprofen or amino acids, for whatever reason out in life, L is the one that is used in life. R typically doesn't do anything. So like I could have the left-handed version of ibuprofen and it might actually help my headache, and then the right-handed version doesn't. So what happened with the thalidomide babies, you might remember, they did some experiments, and I think it was mice, I'm assuming it was mice, they tested it and they figured out that one of these versions of thalidomide, the right or the left-handed version, caused birth defects in the future offspring of mamas. And so as long as you gave them the right version, everything was cool. Turns out in humans, we actually have an enzyme that will flip between these just randomly. So you can give us, let's say that this was the okay version to have. If you give mom this in a mouse, it stays that, and the mom doesn't have babies with birth defects. But if you give this to a human, there's an enzyme that flips it back and forth between this version and this version. And this version, let's say, is the one that means your babies are born with limb deformities. So in humans, just changing, back to my analogy, you have some structure. This is fine. This is a birth defect in your unborn child. Pretty crazy. We are going to stop there for today with lipids. Our next topic will be proteins and enzymes. Thanks for playing.